Know if you can see my screen. Awesome. Okay. Now you can see full screen, right?
Not in the full
Not in
present.
presentation mode.
Yeah,
No?
here you go.
Okay.
Yes.
Okay, so thank you for the invitation. Thank you, Shindan, for the introduction. Today, I would like to talk to you about some of the work that I've been doing in collaboration with Methansat and Tempo team. My talk is called Deep Learning Method for Space-Based Hyperspectral Monitoring. So, as Shindan said, I came from computer science field. I moved into atmospheric science kind of recently. So I would like to take this slide in order for you to show what is my background and where the ideas that I'm going to show you came from. So my interest is machine learning. So basically what I do is to take some data, let's say X, and pass this data through a function f of x, usually deep neural networks, and try to make this neural network to learn something useful in order to then use any other sample from this X distribution and be able to approximate a function Y. This X distribution usually, I started by taking astronomical data as my main background. So I work with time series, I work with images, I also work with text. And then I move into the geospatial domain. I lead an initiative which was aimed to predict some trees into forests in order to make conservation efforts. And it was in this point where I figured out that some of the methods that I was using for astronomy, especially for spectroscopic observations, whereas were useful for what I believe is one of the most important and pressing challenges we have now as humans, which is climate change. So this is what I am now working on. One of the problems that I'm facing are the methane retrieval. As most of you know, methane is a potent greenhouse gas with a warming potential 80 times higher than CO2 during its 20 or 30 first years of release, making it a great target for near-term mitigation effort. Other way to see this is if CO2 is how much global warming we have, methane is the rate at which we get to this global warming. So making efforts to mitigate methane is a pressing challenge for us now. There is where methane set came to the field, because methane set is a mission that aims to do both things, mapping high resolution large areas with a large spatial coverage, and also be able to map emission from a specific point sources using a low spatial resolution. So MethaneSat has an airborne companion, which is called Methane Air, which is basically an aircraft, but are both equipped with the same spectrometer sensors. One is the O2 spectrometer sensor, and the other one is the methane spectrometer sensor, which operates between 0.59 to 0.69 microns approximately. So both methane air and methane sat operates at different levels of processing we are going to use in this work. The first level is level 1B, which generates calibrated, corrected, and georeference data, which consists in these hyperspectral cubes, which represent each pixel represents measurement from a specific wavelength, and the full hyperspectral cubes covers this full spectral signature from seeing 1.68 to 1.68 microns. Also, we use the level 2, which consists in vertical column densities of methane and CO2, along with the surface pressure retrieved from the O2 spectrometer sensor. This surface pressure is compared with an a priori surface pressure we compute using and assuming a cloud-free atmosphere. And the features we obtain from this a priori measurement compared with this real surface pressure we obtain pass through a naive-based classifier and allow us to obtain the cloud product, which consists basically in cloud masks derived by a cloud fraction and also cloud shadow masks. Also, we have a level 3 in which we have a common grid in which we map a lot of different passes from both the satellite and the aircraft. And it consists in column average dry mole fraction of methane, basically the concentrations of methane we have in the specific areas. And then we apply a method that I'm going to explain in more detail later in this talk, which we call the wavelet method, in which we obtain, with which we obtain these methane plumes retrieval to individualize each of the methane emissions. So this is the visual outline of the things that I'm going to talk today. We have the two satellites, MER and MSAT, and we are going to tackle two challenges. The first challenge is cloud and shadow removal. Cloud and shadows create atmospheric artifacts that generates that that does not allow for accurate methane retrieval. So one crucial first step is to remove cloud and shadow for the scene in order to make better retrievals. And the second one is the methane plume detection. We are going to talk about a lot of methods and also combination between each of these methods. I don't go in much detail, but I would like to cover everything in the detail we need to understand everything. Please, if you have any question, ask me. Yeah, just interrupt me. So this is the data set we have for the cloud and cloud shadow tasks. It is composed by METHANER and METHANSAT hyperspectral samples. We have something like 500 and 26200 hyperspectral samples from each one. Therefore, we are in the setting of few label samples. Usually machine learning model takes more samples to learn, so one of the things we need to tackle, a great challenge in this, is to be able to train these machine learning algorithms with these few labeled samples. The spectral range we are going to use, as I said, are between 1.5 and 1.6 microns. We have little differences between the spectral range between METHANER and METHANSAT, are little differences, but does not allow for directly transfer from one mission to the other one. So we are going to explore both missions separately. And also for METHANSAT, we have 4 classes: cloud shadows, dark surfaces, and background. And for METHANSAT, we have just 3: cloud shadows, and background. We don't have dark surfaces in METHANSAT mission due to the difference in resolution. So the first thing we did was to create this method, which we call ILR, Iterative Logistic Regression Method, which was presented to the NeurIPS workshop for tackling the climate change in 2023. What this method does is to basically select some specific bands that are most useful for cloud and cloud shadows classification. The idea is to take, to sample from spectral, each pixel from the image individually. We take the full spectral signature, and these X1, X2 to XM represent the measurements at the first index of the first wavelength, second wavelength, up to the M wavelength. And those are multiplied by corresponding weights. And we compute the logistic regression loss function. And the idea is to classify between each of the classes we have. And then what we do is to, based on the weights, take the higher weight in absolute value. It should be the most important weight. Therefore, it is associated with the most important wavelength to perform the classification. We do this iteratively, so we extract up to 30 most important wavelengths for doing this task. And then we train a final iterative logistic regression with the most important bands in order to obtain the final classifications. A second intuition is use an MLP, which is basically to create different logistic regression methods. We can imagine each of these circles, neurons, perceptrons as individual logistic regression methods. So we have many of them, and the intuition is, as these MLP models are universal function approximators, they should be able to decide by their own what to suppress and what signal to suppress and what to let it pass in order to make the predictions more accurate. So this is the second method we use. Also, just not only to taking into account the spectral signature, we use a spatial method, which is called UNET, in which we have a convolutional neural network that computes feature maps from the full hyperspectral cubes. So we have an encoder architecture which decreases the spatial dimensions of the input, but also increase the length of the feature maps, and we have a decoder what decrease the length of the feature maps and increase the spatial dimensionality in order to go back to the original input dimension and obtain the final segmentation map. So this is a very common method, and we established this as a baseline to compare our algorithms. We also use some state-of-the-art vision transformer architectures in our work. Basically, what this architecture does is to take code these hyperspectral cubes into patches and project them into vectors that are a fixed length we choose. These vectors are concatenated or summed with a positional encoding to preserve the order of this vector in the images. And they are passed through this transformer encoder, which is composed by n of these kind of layers. In these kind of layers, we have the multi-head self-attention. This mechanism is a little bit more complicated, but what basically does is allows each of these vectors, which we usually call tokens, to extract information from every other token. So that's what we call attend to every other token, extract information from them and aggregate them. So we pass this, the output of this multi-head self-attention layer to a layer norm for allow for better optimization, and then through a linear layer that aggregates all the information we extract from the multi-head attention together. So we have n of these layers, and we select some of these n layers and pass information from these layers to a segmentation head, which is basically other convolutional neural networks that increase the dimensionality, and finally we obtain the feature map with the probabilities for each of the classes we want to classify. Other cool idea is we can use exactly the same architecture, but different data. Specifically, we can use spectral former for computing attention in the spectral signatures. So what we can do is to take an individual pixel, divide this pixel into patches of signals at some ranges of wavelength, and project them using the same projection layer into these tokens. We add to these tokens an extra token. We call this extra token class, the class token. We also add the positional encoding with the same architecture. We intuitively allow this class token to extract information from every other token in the sequence. And then we take this class token in order to classify pixel by pixel. So taking all the pixels of the images, we finally obtain the predictions for the segmentation model. This is the method we propose. We propose something much simpler than what I showed before. The method we propose in this work, it is called a spectral channel attention network. What this method does is to aggregate the information spatially and create an spatially average spectral signature that is basically the mean across the spatial dimension at every wavelet. We pass this aggregated spectral information through an MLP layer, and we compute a spectral channel attention, which is basically numbers that are bound between 0 and 1 using a sigmoid activation function. And the spectral signatures are individually multiplied by these spectral channel attentions. The intuition behind these methods is to compute and let the model to specifically learn what bands it has to highlight and what bands it has to suppress in order to perform this segmentation task accurately. We do that for each pixel individually in order to obtain the full segmentation map. So it is much simpler method, and as we are gonna see later, allows for better generalization under few label samples. So as you can see here, we are taking each pixel individually. We are taking just the spectral signatures, so we are not aggregating spatial information, and there is a lot of redundancy in this spatial domain. So other idea we take is to combine two approaches, the approach that specifically and explicitly takes into account the spatial characteristics of the images, the unit, use a train unit in order to obtain a prediction, use a train scan in order to obtain a prediction, and combine the prediction of both into a unique and single prediction that will be our final prediction. We can do this using an MLP and also using a convolutional neural network to better take into account the spatial characteristics and redundancies in the image. So this is the general results. As you can see here, scan and unit are the best performing methods along with the individual methods that I've showed you. Particularly for meth and SAT, scan is the best performing one. And as you can see here, in combination, using the combined methods, we obtain the better results that, and we have larger gains in terms of performance by a large margin. So we are, this tells us that we are indeed extracting some specific information from a scan that is not extracted by unit and vice versa. So both in combination works pretty well. Also, we compute the results using the vision transformer architecture that I show you and the spectral transformer architecture that I show you individually. But well, basically they were hard to compute. They were costly to compute using these hyperspectral cubes. Trainings often were days long. So, and also the results we got from both architecture were not satisfactory. So we just let this baseline we compute this baseline on Methansat, and we go now any further than that. with those methods, but here we can show that scan basically outperforms classical self-attention method in this scan under this few label constraint. Here are the visual results. So as you can see here, there are some difference between the prediction of unit scan. I think this one where I have my cursor is the best example. But basically, scan generates better boundaries around the predictions. UNet tends to generate more blobby or over smooth predictions and tends to overestimate the boundaries for the prediction, while scan is better at generating these boundaries. But UNet has a better spatial consistency as it takes into account not only the pixels, but also their neighbors. So both in combination have the best of both worlds, generating both great spatial coherence and also great boundary delineation. Here we have a preprint of this work that I showed you. If you want to take a deeper look, this was also accepted to the NeurIPS conference on tackling the climate change, and we are going to present it in 2 more weeks. Just to show you, in terms of computational performance, despite these methods are not always that take time to train, always minutes to train, and for many epochs, always hours to train. The inference is super fast. So for 1,000 square kilometers, we usually take only milliseconds, a few milliseconds in order to make inference. So also the method we have explored allows for real-time computation in many cases. Other thing we are also doing is extending this work on the tempo data. So we have now some preliminary results, but the problem is for tempo data, we only have cloud masks, but not cloud shadow masks. So what we are doing is to create our own labels, basically taking the B-wind and solar zenith and azimuth angles we create, and having knowledge of where the cloud is, we create this mask which tell us where the maximum extent of a shadow could be, and then using cloud fraction, selecting this area that potentially a shadow could be, and also lower cloud fraction threshold, we generate very good labels for these shadows, cloud shadows. So again, scan is the best performing one for this task, outperforms the UNet model, even while UNet was trained on RGB images. So we have lower dimensionality. Here we have more than 1,000 spectral bands. In RGB, we have just three. So one may expect that due to the course of dimensionality, UNet outperform the rest of the method, but it's not like this. It outperforms UNet using full spectrum, but not scan, which is also good. And we are just using 70 samples. So these are very preliminary results, and we are doing very well. So good news. Now we're going to talk about the plume detection, in which we go from L3 to the plumes, methane plume mass. So having removing the cloud and shadows, so we have no artifacts, effects within the images, we apply the wavelet method, which basically take these L3 data signals, these methane concentrations, and use a 2D wavelet transform in order to enhance and reduce the plume and noise signals. Therefore, enhancing the plume signals and reducing the noise signals, we can then create a threshold in order to label and create masks for our methane plumes. This is ongoing work, so this is what I can show you for now, but basically what we generate is this kind of masks here, where we have clearly this plumes enhancement and its respective plume masks. So we performed some initial exploration with an exploratory data set with just few scenes, just few samples also, 43 scenes specifically for methane air, with approximately 300 methane plumes, and 11 scenes from L3 data with almost 60 methane plumes. And we take the full scenes and we create patches of 224 by 224. And we only took patches that contains plumes inside in order to train our models. So we can do two things. As I show you, we have this semantic segmentation scenario in which we want to predict a class for every individual pixel in the image. But there are also other kind of segmentation, which is called the instance segmentation. And the difference between semantic and segmentation and instance segmentation methods is in instance segmentation method, we also individualize is each of the detections we make for the image. So instead of having only plumes or background or person and background, we have each individual person and the background, or each individual plume and the background as the classes. The method we usually use for instance segmentation is called mask-RCNN. It's the most known method for this kind of task. And what this method does is to use any computer vision backbone as a feature extractor. It could be a ResNet convolutional neural network or the vision transformer that I show you. Also, a mask autoencoder, which can be pre-trained beforehand. And the idea is to extract features using this backbone, and we obtain this region of interest. Using this region of interest, here we are showing 4 regions of interest, which represent these squares here. We pass each of these regions of interest through a neural network with 2 branches, one of them computing labels for the semantic segmentation task for this region of interest, and the other branch computing classes, the class probability, and also performing regression in order to get the bounding box of this prediction. So it is like mixing both semantic segmentation and detection together into a single framework. So this is basically instance segmentation. So in the initial exploration we did for methane air, we compare both settings, UNet versus mask RCNN with different backbones. We use the ResNet backbone architecture, the vision transformers, and the mask autoencoder backbone architectures for these results, and we conclude using methane air that the master CNN using the ResNet backbone architecture outperform the rest of the model by a large margin. What we need to see here is probably the F1 score. We have a very unbalanced data set. So as you can see here, the F1 score of this architecture is much higher than the rest of the method. What we are showing here are the results transforming basically the outputs of the masker CNN, which are individualized, but into a binary classification in order to compare it with UNet. They are different tasks, but we transform the outputs into a similar objective in order to compare them together. Also for MethaneSat, we did the same, but also as we had previously trained these methane air models, we perform fine-tuning. That means takes the pre-trained method on methane air and and use this pre-trained method as the initialization for training with MethaneSat data. So basically, the same pattern repeats again, but now the difference is with fine-tuning, we are able to obtain rate margins of advantage here. So again, our Mascar CNN ResNet architecture seems to be the most suitable for this kind of task. And also we have the advantage that allows for individualization in the detections. So these are the results of the unit. So as you can see here, here I have the data, the real mask, the run through, and in the right we have the predictions. As you can see, our unit architecture tends to over predict the amount of plumes we have, having a low precision. That means we have a high amount of false positives within each scene. And most of the scenes that should be predicted as background are predicted as plumes. It is our master CNN ResNet architecture. So as you can see, the predictions are much better than in the case of unit. Our model tend to capture where the shape should be and what this shape should be, and it tends to generate very well delineated boundaries. As you can see here, the precision and the recall are higher than 0.8, so this is super great for this kind of tasks. In the case of the vision transformer architecture, we obtain no much good results. What this architecture tend to do is to create fragmented predictions within the scenes. So as you can see here, there are a lot of fragmented false positives that are generated randomly within the images and does not match with any particular enhancement or probably noise. It's very much predicting randomly, so it's not performing that good. But an interesting thing is when we use a masker CNN approach, which basically is pre-trained by taking input patches, masking those input patches and training a model to predict what is in these masked patches, like here, in order for the model to understand some semantic characteristics within the image. We obtain better results. We now obtain masks that at least have sense. We clearly see that there is enhancement here, and it has a tail that in the ground truth is not present. But here our model is able to predict this tail. Of course, this method is not as good as our masker CNN with the ResNet backbone architecture, but it's doing pretty good at this point. So some of the conclusions we have now is first, deep learning architectures for cloud and shadows achieve much higher performance than the usual methods such as this logistic regression method that I showed. Unit and scan are very good. Unit in spatial coherence and scan in boundary precision. Scan tends to be better for shadow under surfaces, while unit tends to be better for clouds. And both in combination generates the best results overall. So they both are extracting different and seeing different characteristics within the images. So when we combine what both of them are looking into the image, we obtain higher performance. Also, masker CNN and ResNet seems to be a suitable option for plume detection, especially again in this setting where we have few label samples. We don't know yet what happens when we have a lot of label samples, but at least in this set with few label samples, it seems that it's very suitable. So some questions or some future work we would like to tackle is how can we scale this scan method and masker CNN with more training data? What happens? Does the same patterns repeat when we have more data? Or are the transformer architecture or became the transformer architecture much suitable for this kind of task? We don't know yet. Also, in the methane plume detection, what happened in full scenes, as I show you some patches that contains plumes inside, but when we have full scenes. We have patches that not contains plume inside, and some of these patches may be super noisy. So how can we deal with this noise and also with the diffuse part of the plumes that also cause some troubles to our network architecture? Also, we were measuring, as I say, the performance at the semantic segmentation task, transformer the masker CNN predictions into semantic segmentation prediction, basically binary maps. But what happened when detecting individual plumes, what amount of false positive, false negative we obtain, what are the characteristics of the plumes we are missing. This is something that remains incomplete. And also what happened when we apply physical constraints to the predicted plumes. Are we able to improve the detections adding these physical constraints? And finally, this is like a more long-term question. What happened, or are we able to directly, in a single pass, go from the L1B radiances to the mask? What we answered was what happened when we go from L1B to the cloud products and when we go from the L3 data to their mask. But what happened when, can we directly go from L1B to the masks? It is something that it would be awesome, but we need to figure out how we can do this. This is a little bit how I imagine the machine learning architectures. At this point, it seems most of the applications of machine learning, deep learning for this kind of atmospheric data relies in machine learning methods that are trying for specific missions. But how I see this is having a single unified machine learning method that not only allows to use any kind of sensor, any kind of satellite, or even ground-based measurements, but also perform different tasks such as cloud detection, methane plume detection, tree detection, or whatever. And also learn the relationship between each of these detection and what happened with tree, what happened with the environment, uh, with when trees change and so on. So this is how I imagine. This is one of the things that I would like to tackle also in a PhD program. Yeah, I think this is all that I have to talk to you for now.
Thanks, Manuel. It was a great talk. Let me
Thank you.
stop the recording.